Okay, so this P1 video is about seafloor spreading and plate boundaries. And we're basically going to start off with seafloor spreading as an example of something that happens at a plate boundary, and then go over the different types of boundary. So what we've got here is a simple diagram of the plate boundary, and this is a cut through the Earth. So we've got the sea on top, the ocean crust at the bottom of the ocean is the brown layer in the middle, and then underneath that the mantle, which is, if you remember, solid rock but extremely hot and able to flow to a certain extent. So what's the cause of seafloor spreading then? Well, basically seafloor spreading occurs at ocean ridges, and what we have is convection currents in the mantle. Now, a convection current is basically the movement of the mantle because it's heated from underneath by the core. So it's actually a radioactive decay inside the core that drives this heating process, and you get certain parts which are hot spots, and over these hot spots in the core you get the convection currents in the mantle. And that's a bit like the movement of the wax in a lava lamp. Okay, when it gets hot it moves upwards, it decreases in density and floats up to the surface. And so the yellow arrows here represent the motion of the mantle, and it moves upwards and then sideways, and this sideways movement drags the plates apart. Now obviously in reality there's not a massive great big gap in the middle here, otherwise the ocean would just flow in onto the mantle. So this process is happening gradually, but in order for you to be able to see it, I've massively exaggerated the amount of movement that we get. And what basically happens is that as the ocean crust moves apart, dragged by the currents underneath it, it drops the pressure underneath on the mantle, and that allows the mantle to just liquefy a little bit. It turns from a sort of solid and melts, moves up into the gap, and obviously meets the ocean, which cools it substantially. So as it cools, it forms into new rock, and so now we have a new section of ocean crust been made. It's worth noting, therefore, that next to this ocean ridge, the rocks near the ridge are very new, and as you move further away from the ridge, the rocks get older and older on either side. Okay. This process repeats continuously. It goes on again and again and again, and this leads to a spread rate of, at most ocean ridges, of a few centimetres a year. It varies from one to the other. So the Mid-Atlantic ridge, a few centimetres a year, is reasonable. Okay, so that's seafloor spreading and the causes of it. We're going to come back at the end of the video to look at magnetic seafloor striping, because that's only really essential for those people doing higher tier. So what other types of tectonic plate boundaries have we got? Well, we've just had our ocean ridge, which is oceanic crust with the plates moving apart. It's also called a constructive margin because we are forming new rock in the gap there. So the three others that we're going to cover is an example of a destructive margin, where oceanic and continental crust move towards each other, and we'll see the details of that. Continental plate boundary, where two thick continental plates are moving towards each other and creating mountains. And then finally what we call a conservative margin, where the plates aren't destroyed, there's no creation or destruction of new rock, but the plates move past each other. Okay, and this can cause earthquakes. So we're going to deal with these one at a time. So first, the destructive margin. Well, what we have here is the ocean crust again, just similarly to before. This time we have a very thick continental crust. I've shown the mountains already formed here, but it's basically this process of the ocean crust moving under the continental crust that causes the mountain formation. Okay, and similarly to before, we've got the mantle underneath. So what's going on then? Well, the mantle again heated by the core below it, and this time we're sort of looking at with the ocean crust being pushed towards the continental crust. So you could quite happily imagine over here on the left-hand side of this diagram that there is an ocean ridge here, because this convection current looks exactly the same as the one that we had under the ocean ridge. Okay, so it's important to realise that whilst we're looking at these things separately, at one edge of a plate there's going to be rock being created, at the other edge there's going to be the rock being destroyed. So the total amount of crust on the surface of the Earth isn't changing, we're just sort of creating in one place and destroying in another. So the next step then is the mantle gets, the motion of the mantle, the movement of the mantle drags the denser ocean crust underneath the continental crust. So this ocean crust sinks underneath here, and there's a lot of friction involved in this process as the two rub together. So you do get some earthquakes as well at these boundaries. Okay, we'll talk about the process of earthquakes a bit more when we look at the conservative margin. And as this friction kicks in, it melts the ocean crust as it moves underneath the continental crust. And then what happens is that the melted crust, okay, also is heating the mantle around this place, and we get a molten rock underneath this continental crust. This region where the ocean crust moves underneath the continental crust, by the way, is called a subduction zone. Okay, so the friction's melted the rock, and that hot rock then rises upwards, and we get it coming to the surface and out of the top of the volcano. So the hot molten rock rises up through any sort of cracks in this continental crust, forces its way through. It might take some time to do this, okay, and erupts from the top. This magma erupts from the top of the volcano, becoming lava. So that's the process that leads to volcano formation, okay. Okay, so we've now looked at the ocean ridge, constructive margin, the destructive margin, at the boundary between an ocean plate and a continental plate, where we do get these mountain building, volcanoes and earthquakes. Okay. So, the continental plate boundary, well, we start off with two big, thick chunks of continental plates. I've left a tiny bit of ocean crust between them to illustrate this point. I mean, this is the classic example of this type of margin is the Indian plate driving up into the Eurasian plate and making the Himalayas. And so what happens is, again, convection currents, this time driving both of these plates towards each other. Okay. And because the continental crust doesn't really have anywhere to go, it just sort of wrinkles and builds these mountains up. It crumples together. The mountains are built up from the thick plates. Okay, and interestingly here, because the rocks that now are at the top of these mountains were the ones that were originally in this small piece of ocean crust between the two continental crust tectonic plates moving together, you can find things like fossilized marine life, so sea fossils, fish, small sea-dwelling animals at the top of these mountains, and you can find these at the top of mountains like Mount Everest in the Himalayas. So there's very strong evidence there that this process is taking place. Okay, so we've got our first three, and now our final one. We're going to switch view a little bit. All the previous three have been sort of a slice through the Earth looking from the side. We're going to look at the conservative margin top down. So I've coloured the two plates different colours just so you can separate the two of them. There's no significance to the colours. They're just two different plates moving past each other this time. So what's going on here is they're trying to move past each other. So the arrows are showing you the direction that the mantle is. Again, the convection currents in the mantle are trying to pull these plates. But they're getting stuck, okay? And we can think about it really as they're getting stuck mostly at this yellow dot here, okay? So something is catching, the plates are unable to move past each other, and in practice they may get sort of stuck at several points. It's the incredibly large amount of friction that's stopping this from happening. But the convection currents in the mantle are still trying to drive them, and as the strain increases between these two plates, we get a build-up of elastic potential energy, just like you would if you were stretching an elastic band or stretching a spring. And eventually, the plates can't take the strain, and they slip past each other like that, and move significant distance. And at the place where they were mainly sort of jammed, we get the earthquake occurring, and so the red circles there were the shock waves expanding out from the earthquake centre, and that we call the epicenter of the earthquake. Okay, so it's this process of build-up of elastic potential energy and sudden slippage of the plates that leads to the vibrations of the earthquake. Okay, so there's our four types of tectonic plate boundaries that we need to be able to sort of describe and know something about. And we're now going to look in a bit more detail at back at the ocean ridge for this idea of magnetic seafloor striping, which is really the piece of evidence that finally convinced people that continental drift was happening. Okay, it didn't really happen, this discovery, until the 1950s. So, to properly understand what causes the magnetic stripes, there are two facts that you have to know. Bearing in mind this is now higher tier stuff, so if you're doing the foundation paper, it's probably not necessary to watch it, though you should try, just so you can try to understand it. Two key facts that you need to know, but you don't need to understand how these things work, and it can be difficult to accept, right? So you need to know that the Earth's magnetic field flips from time to time. So compasses currently point north, right? During the time of the flip, the compass will turn round, and after the flip is completed, it will point south. This happens very unpredictably. It happens every 100,000 years to several million years. You'll see some data at the end of the video which shows you how irregular this is. So it's a very unpredictable, very chaotic process. So that's number one, field flipping. The Earth's magnetic field flips over. Okay, compass is reverse direction. And the second thing is when molten rock cools and forms solid rock, it kind of records the magnetic field around it. So if we're in a period of time where the Earth's magnetic field is pointing as it is now, the rock would become magnetized, so it was acting like a magnet that's pointing north. Okay, so if you brought a compass near to that rock, it would distort the direction of the compass needle. Right, it would make it point along the direction that the rock was magnetized in. But once the rock is solidified, so it forms, as it's forming, it picks up the magnetic field, right, and it records it, and this is due to sort of iron in the minerals in the rock, and iron is magnetic, so it's just the same way as if you get a magnet and stroke it along an iron nail, you can magnetize the nail. It's the same sort of thing that's happening here. But the key thing is, once the rock is solidified, that magnetic field is stuck in the rock. It's stuck, magnetized that way. The only way to get rid of it would be to melt it again. Okay? So, those two key facts are vitally important. And what we're going to do is we're going to overlay those two facts onto our original picture of seafloor spreading and see what it produces. Okay, so what we have here is, I haven't labelled everything like we had before. I've labelled the ocean ridge. We've got our seafloor spreading happening again. In the top left corner here, we have our compass to show us which direction the field is in. Okay, at the moment, the yellow side of the needle is pointing north, and I've called that normal magnetic field. That's the field we've got at the moment. Okay, and when the purple side of the needle is pointing north, so when a field flip has occurred, this will flip over. We'll have what we call reversed magnetic field. It's the opposite to normal. So now what we do is we form our new rock, and with these two other processes going on, the field flipping and the magnetization of the rock. I've left the current ocean crust as brown. You should note that doesn't mean it's not magnetized, it's just we're concentrating on the new rock that's formed. So the stripes that we're going to see in a second will exist in this brown layer already, right? But I didn't want to complicate what was going on at the ridge. So here we go. Same as before. The convection currents pull the ocean crust apart. The new rock forms in between. And this time we've colour-coded the rock yellow because this rock has solidified and formed when we have the compass needle pointing, the yellow part pointing north like it normally does. So that rock is normally magnetised, we call it. And then, say that probably has taken hundreds of thousands of years to form that amount of rock. It's happened very gradually, remember, not all at once. And then the field flips, and again, you don't need to know why, but the field has flipped round. So now, when we move the rock apart in the centre here, the new rock that forms is going to form magnetised in the reverse direction. So we've got reversed magnetised rock here. It's the opposite way round to these. So if we put the compass needle over the yellow stuff, it would point north. If we could put the compass needle near the purple stuff, because it's magnetic, it would point south. Okay. Note the rock that's formed already is unaffected. It's solidified. We can't change its field direction, its magnetisation once it's solidified. So the same thing keeps happening. I'll show you one more time. The field flips over, so watch the compass. There it goes. It's flipped over. We form some new rock in the middle. Okay? So this new rock is now formed magnetised in the normal direction because it's flipped back again. So we have this yellow section normally magnetised. And this keeps happening, so we'll get yellow, purple, yellow, purple. Now, please be clear, they're not actually coloured yellow and purple. That is only indicating the direction of the magnetic field. There is no visual difference between these rocks at all. The only way you can detect it is by putting a very sensitive compass on top of the rock. On the yellow rock, it will point north. On the purple rock, it will point south, okay, as it's coded on there. So that's what it looks like from the side. If we're looking at it from above, it kind of looks like this. Looking down on it, the white line's the ocean ridge, and you can see the pattern is symmetrical either side of the line. Okay, so this is a key characteristic here that proves that the rock is spreading out from the ocean ridge. You see this symmetrical pattern in the magnetism when you measure it with the compass. Okay, they had very sensitive compasses on submarines to try and they were trying to detect. The US Navy was trying to detect enemy submarines using magnetic fields, and instead they detected this. Okay, so And just remember as well that the further away from the ridge, the older the rock is. So what we've got here is a history of the flips of the magnetic field in the Earth, right? With now being the ocean ridge, and as we go further away, hundreds of thousands of years between these flips, we have a record back millions of years of magnetic field flips, which we're going to see in a second. So that's the process of the magnetic field flips forming. A really useful thing for you to be able to do, I haven't included a summary of it here in the video, is to watch this section again and try and write your own summary. Okay, write your own summary of what's going on, bullet point it, so that if you get asked this in a 6-mark question, you have it there and ready. Okay. So, just a note on the fact that the real data, as always, doesn't perhaps look quite as neat as we hope it to. The diagram here on the left is just a record. This is looks like a barcode, and this is taken from ocean crust, and you can see how irregular the flips are. So recently we've had a fair number of flips fairly frequently. The black is what is magnetized normally and white abnormally, but there's some sections here, a 40 million year chunk where it didn't flip at all. Right, so this is an extremely random, chaotic process. The other thing to note, if you look at the real pattern of stripes, because the ridge is not necessarily moving apart at a constant rate, or a constant rate even along its length, then instead of a very clear set of stripes, we get this slightly sort of speckled effect. But you can still clearly see the sort of symmetry. There's a bit more on the right-hand side. This stripe on the right-hand side here, about sort of 7 or 8 million years ago, wider on one side than the other. And there are various reasons for that variation. But if you look across the whole record, the symmetry is maintained enough that we are confident, okay, that the motion of the seafloor and this magnetic forming process, this process of forming magnetic rock, is the only thing that can explain this pattern. And so that is clear indirect evidence that the continents are moving. Okay, it's not direct because we haven't actually measured them moving. We haven't got, like we can do, GPS devices, put them on either side of the Atlantic and measured the very slow motion, this sort of few centimeters per year movement. But it's the best indirect evidence we have. Okay, very difficult to argue with this, and it was the thing that finally led to Wegener's theory of continental drift really being properly accepted.